We'll finish up this last additional topic. It's not an additional topic. You've already seen a bunch of it, but I thought it'd be fun to go into a little bit more detail. And at the end of today's lecture, we'll talk about just summarizing the whole class and what do you do now, where to go from here. So, okay, so jumping back into this. So we were talking about, cardinality constraint, but the cardinality could be applied, for example, to the, let's say, a first difference, in which case you would be doing piecewise constant fitting, and that's kind of obvious. I mean, you take a first difference matrix here. So you take a first difference matrix D, and then if dx has a small cardinality, it means you have a small number of jumps in x, right? And you could just do this for the second difference and things like that. If you do second difference, then you get a second difference matrix, and if this matrix multiplied by x is sparse or has cardinality less than k, then this is exactly when x is piecewise linear, or I guess that's the way people would normally say it. I might say piecewise affine with something like k kinks in the piecewise, then change of slope and stuff like that. So that would be it. So we can handle all these kinds of constraints with in this convex cardinality framework. Okay, so now we get to the heuristic. You know it already. You've seen it. It's really dumb. It's wherever you see like the cardinality, replace it with a multiple of the one norm, right? Or just add some L1 regularization to the objective, right? And then gamma here is a parameter that you use to achieve the desired sparsity, right? So that's sort of the heuristic. You've seen this a lot. There are some other versions. You're going to see them. They're actually better. There's weighted L. That's a weighted L1 norm. And this one, I've heard people call that an asymmetric L1 norm, but I hate that because it's not a norm if it's not symmetric. In other words, you actually would penalize things being small or less than zero, bigger than zero, differently with different slopes. By the way, we're going to see later exactly why you might do that, right? So this is, but generally speaking, it's just the L1 norm heuristic. And it's used in a lot of fields. So, here's the minimum cardinality problem, and you start with this problem that's hard, and you replace it with this one, which is convex, and so it's easy to solve. Now, of course, that's just a heuristic. When you solve this problem, you have not solved that problem. This is merely a heuristic, a quite good one, in fact, for solving the top problem. Okay. If you had cardinality constrained problem, lots of ways to do that. One way is to literally just replace this with an L1 norm and you have something that looks like this. Or you can make it an L1 regularization. You can actually add this regularization term to the objective. And then you adjust beta and gamma until the cardinality is what you want. Right, so these are sort of, the most basic ways that people might do this. Something called polishing is actually super interesting. That's this. What you do is you use an L1 heuristic to guess merely the sparsity pattern of x, if x is the thing you want sparse, right? So you run an L1 heuristic, adjust gamma until you think there's supposed to be 15 non-zeros or you feel like that's right for you. Then you get 15 non-zeros. What you simply do is you record the locations or the indexes of the non-zero entries. Okay, so this is phase one. Then you go back and you resolve the problem with only those as the variables. All the others are now zero, right? And you remove any regularization if you had that, right? So that's called polishing, right? So this would be very, very commonly done, right? Actually, it's interesting. If you ask two different people who do statistics, is this a good idea when you're doing model fitting? And most of my friends will say, no, you should never do this in statistics, right? Because the whole point was you not only did you do feature selection, but you shrunk also the coefficients, right? So and then other people I know, they would say, no, we always do this. So I'm not quite sure. I mean, I think it depends on the application. So an example of where this is always done is when people do, they have gene response data. So you have 20,000 gene expression features, and you're trying to predict something. So first step is you do L1 regularized logistic regression. You find the 22 genes that you believe will give you a good logistic model, right? Again, if you know what I'm talking about, that's fine. If you don't, that's also probably okay. So you get these 22. You locate those 22, then you go back and you just fit a logistic regression model with just those 22 genes. Everybody got that? So, yeah.
Is the sparsity pattern dependent on the initialization? Like, would you get like a different sparsity pattern?
Absolutely not. No. No. So there's no such thing as initialization, number one. And number two, if it turns out when you solve that problem, there's not a unique solution, which is entirely possible, then it's possible that you could have different solutions, but they'll all have the same optimal value, right? So, but no, that's not an issue, right? If that's an issue, we're in deep, deep trouble, right? Because the general story for convex optimization goes like this. I've done this, I've gone off and give talks about something, and I'll say that's a convex problem. And then I'll just say, we can solve it. And then people will say, how'd you solve it? Did you use conjugate gradient? Did you use this? Did you use the interior point? I'd actually literally just say, it's none of your business. It would irritate, it's very good at irritating people, right? And then finally they'd say, but you must have used a method. I said, I used a method. I did. You're right. I did. But I'm not saying what it is because it's not relevant, because this is a convex problem, right? So what that means is basically I told them finally, I can think of 50 methods, all of which would work. All of them. So why would, it's like if somebody does least squares and you go, how'd you do it? How'd you do it? Did you use QR factorization, SVD, conjugate gradients, LSQR, right? And the answer is like, unless the problem is ginormous and you're under extreme real-time constraints or something like that, it's no one's business. They would always get the same answer. So that's why, and certainly it has nothing to do with the initial condition. So that's just my reaction to that. Okay. Okay, so this is polishing. I mean, it's interesting, and it depends on the application, right? So whether or not you should do polishing. I think in a lot of statistical fitting methods, you should not, because the entire point was to regularize, right? Well, it was two things. It was to do feature selection and to regularize. So you shouldn't do this. Many other things, like if you're doing electronic design or mechanical engineering or something, and you want a sparse thing because you don't intend to build a space frame with 1 million bars, but in fact only 236, then you do this, because why should you once you know which ones are actual bars, then you go back and solve the problem, right? So okay, that makes sense. So now we're going to give a couple of we gave a couple of interpretations as to why this L1 heuristic would work, right? And one that is not bad is this idea that, compared to a square penalty, an absolute value penalty keeps up the pressure to make the thing small all the way up until you get to 0, right? And by pressure, I mean the derivative is like, is either plus or minus 1. It's plus 1 if you're negative, right? Whereas for like a square penalty, once you get small, it doesn't care anymore, because the penalty is basically small squared. Okay, so that's actually, believe it or not, perfectly good explanation for why an L1 norm, and for that matter, any penalty with a kink at 0 is going to have this kind of property. Okay? So, in fact, there's a penalty that's very funny. Everyone knows about the Huber penalty, which is, it's a Frankenstein penalty that's quadratic and then transitions to linear, right? So there's another one, which is L1 for small things, and then transitions to quadratic. Everybody picture that? And you're going to get that's going to be a sparsifying regularizer, for example, if you use it as regularize. Anyone, you know what it's called? This is kind of cutesy, but I don't care. That's called the Burhue penalty. Sorry. It's Huber like anyway, it's stupid. Anyway, who cares? Anyway, but the point is that's an example of a sparsifying penalty, right? Okay. All right, so we gave that as an example, and I think you've actually already done problems where you have experienced this sparsification. But now we're going to give a couple of other very cool interpretations, right? So one is let's solve this problem. Let's attempt to solve the cardinality of x, minimize this. subject to x is in a convex set, and then all of the x's are between plus and minus. All the components of x are between plus and minus r. So that's this thing here, right? Okay, so what we're going to do is we're going to write it this. We're going to introduce some new variables, zi, and they're going to be Boolean. They're going to be either 0 or 1. And we're going to write the constraint that xi is less than r is this way. And what this means is if zi is 0, it means xi is 0. If zi is 1, we express the idea that it's less than r, right? So this problem is completely equivalent to that one, right? So they're identical. Not identical, sorry, equivalent. They're not, of course, they're not identical, they're equivalent. Okay. This one is no easier to solve than this, right? Actually, this one you could pop into what are called mixed integer linear programming, so a MILP solver. And you know, if you're lucky, you might get a solution or something like that. Who knows, right? If you're unlucky, you might be waiting an hour or something. So, okay. So what we're going to do is we're going to relax, which is, you know, that makes perfect sense. What we're going to do is we're going to take these z's, which are Boolean variables, so 0 or 1. We're going to relax them to this kind of weird quantum mechanical state that can be anywhere between 0 and 1, right? So that's a relaxation. Now, that gives you this problem here, this top problem. And let's see, let's take a look at it. Oh, good news is that's convex, so that we can solve, right? That's completely tractable. But if you stare at it carefully, you'll realize that, you know, if I divided things out, this is actually the epigraph. The sum of z's here is the epigraph. This is the epigraph representation of the L1 norm of x divided by r, right? So, or just take r equals 1. So this problem, which is literally the Boolean relaxation, it's the relaxation of the original Boolean problem, just simply becomes our L1 heuristic. By the way, this L1 norm here thing was, the L infinity constraint was critical to do this. Without that, the relaxation is nothing. It gives you no information at all, right? This also tells you all sorts, this also suggests all sorts of things. If your variables have different ranges or bounds, then you probably shouldn't be doing an L1 heuristic. It should probably be a weighted L1 norm, weighted by, you know, the inverse of the bounds or something like that. Okay. Now, when you solve this problem, I mean, these are the same. They get the same optimal value. You get you get a lower bound on the optimal value. It's not usually a particularly good one. So this kind of makes sense. Now, you can also interpret this in a really cool way as a convex envelope, which I will explain, right? So if I have any function at all, like here's a function, non-convex, right? Then its convex envelope, I'll just draw it, and then I will write it down. I can write it down in all sorts of very cool ways, right? So whoop, there we go. And then I just do this, right? So this thing, that's the so-called convex envelope of the original function, okay? And it makes sense. So lots of ways to say it. It's the largest convex function that is everywhere below your given function. So that's another way to say it. Here's a super compact description of it, which is very cool. It's f star star, right? So, it's the conjugate of the conjugate. Remember that the conjugate of any function, convex or not, is convex, right? Now, then when I take the conjugate of that, if the original function had been convex, I would have recovered the initial function. But I'm definitely going to get something that is, actually, you can easily show you're going to get something which is a lower bound on the original function, number one. So f star star is less than f is always true. But the other cool part is, had it been convex, you would have gotten f back, right? But so that's actually another way to express the envelope, which I think is kind of cool. And in fact, you'll see a lot of people not even use fenv, but just literally write f star star in papers. That's the convex envelope. So makes sense. And you can work it out for at least some things. And we can actually work it out for the card function, but restricted to an interval. So I'm going to write down the card function. This is 0. So let's see, it looks like this. So that's filled. And then it looks like that. That's the card function, okay? By the way, what is the convex envelope of just card by itself? It has one, and I'd like to know what it is. Yeah, It's just zero. It's the constant zero. And you go, which, if you think about it, A, it's convex, and B, it's a lower bound on the card function, because the card function only has the value 0 or 1. So congratulations. It's completely useless, right? Okay, so, but if we say, no, you know what, but this is I happen to also know that the variable is between, let's say, minus r, right, and plus r. So the actual function I'm taking the card of looks like this, and it goes up to plus infinity out there. Okay, what is the convex envelope of that function? Now, this is actually very cool. You can get it, and yeah, what is it? Yeah, so you just draw, you go like this. I mean, literally, you take the epigraph. The epigraph of the whole thing is this thing up here going up to infinity, plus there's a little needle sticking down here. That's the epigraph. I take the convex hull of the epigraph that fills in this, and then this is f star star. So in this case, where f is card restricted to absolute value less than r. Everybody got this? So actually, it's kind of cool because it suggests all sorts of things. If you had other bounds on x that were asymmetric, you would use like an asymmetric thing here. And by the way, it would be a better sparsifier, right? So this is the idea. So actually, you don't have to worry about that. So for example, in the application of regressor selection in machine learning and statistics, this is generally not a problem because the data have, I assume, standard practice is to actually standardize the features. So they're all now between reasonable ranges, right? Like, in fact, for that matter, probably plus, roughly speaking, between plus and minus 1. And so that justifies the use of an L1 norm. If you, for whatever reason, you did not standardize your features, then, and you want to do something like lasso, then you should, well, number one, you should not do that. Okay, number one. But if you did do that, you shouldn't be using, you should be using a weird, like, weighted L1 norm or an asymmetric thing or something like that. Okay, everybody following this? So it's interesting. Okay. Yeah, so that's just this. If you knew, for example, that if you knew that over this convex feasible set x, if you calculated what's called the bounding box, right? Which, by the way, I could solve for any problem if I don't mind solving 2n convex problems, right? I just maximize xi subject to x and c, and then I minimize xi. So those are both convex problems, and I will get the best possible values of L and U. If x were, let's see, if x has a dimension really small, like 10, you should just consider solving it brute force and like just solve all 1024 convex problems, right? Then is 20, this is actually interesting right here because it's not going to kill you to solve 40 problems to get the bounds, which is going to give you a better sparsifier than just an L1 norm, right? So that would be one. What you get though is something really cool. It's actually, you get a function that matches, it's just what you think it is. I'll just draw the picture over here. It just says, suppose this is between, what I call this, Li or something, and then this is Ui. I'll make it asymmetric. There's Ui, right? I'll just call it U. I doesn't matter. Then this is kind of clear, but your convex envelope looks like this, right? And it's this tilted function, right? Actually, which I think people now call the pinball loss, right? Because I think it has to do with pinball machine. Don't ask anyway. Fine, it's stuck. I think it's stuck. So, okay, that's what this is called, right? So this is the idea. And you will actually, if you do this, you'll actually get you'll get a better sparsifier, right? It's principled. Okay. So now we'll do some examples. Like, the first one is like regressor selection. So here we're doing least squares, but we want to choose here which of the entries. So x represents our parameter in our model, and we want it to have just k non-zeros. So it basically says, here's an example. I'd say here's 25,000 gene expressions. I'd like you to fit a model that predicts some outcome for my 600 patients, you'd say, please, or my 600 experiments with, mice or something, and I'd say, you know what, choose, you can use 30 of them. Go ahead, right? And the whole point there is 25,000 choose 30 is a pretty big number, right? So this would be an example of a regressor selection. Okay, there are lots of ways to do this, and they're all related to lasso, and they have all sorts of other names and things like that, like basis pursued, and it depends on whether it's a constraint or a regularizer and all that kind of stuff, right? So, but this is kind of cool. And here's just a quick baby example where, here's x and R20. So that means, of course, that there's a million different possible values of x, right? Sparsity patterns for x is a million. So we just solved it globally because it's not a big deal. Then you get a trade-off curve of, this is how many features you use, and then this is how small you can make norm ax minus b. This might be some kind of fit, right? And this is a trade-off. This one shows you this is the global optimal, right? This would have been impossible had this been R50. I mean, not impossible but it would be outside this stuff we do in this class, right? And so if you do the L1, if you do the L1 heuristic with polishing, you actually get this, right? This thing. And it's actually really cool. Like often you're just dead on. It's like here it's dead on, and well, that's silly, but here you're dead on. Here you're off by 1. Here you're off by 1, right? So it's actually kind of interesting how this works, right? All right, so this is a baby example, but it's just to illustrate this. It's a huge big difference, right? That the approximate difference in computation effort in this case, we could have done it more efficiently, but in this case, it's 1,000,000 to 1, right? Because each of this point was found. Maybe not 1,000,000, but whatever. This point was found. Actually, it is 1,000,000 to 1, roughly. This point was found by actually checking all 20 choose 4 sparsity patterns and finding the one that had the best fit, right? So it's not a small number, whatever it is, that's it. So the idea that you get this close with, such a stunning reduction in computation, now you can't claim that you've actually solved the original cardinality problem, but that's okay. Yes?
How do you know for sure that the components that are not 0 are the same in both cases?
We don't. Yeah, in fact, they're not, right? Because let's see, which one are you looking at?
For example, the last one, when they match the cardinality, let's say.
You mean like here?
Yeah.
Well, A was probably just chosen randomly, so that has probability 0 of happening. Of course, it is. It's not necessarily true, right? If A had, 2 columns that were identical, right? Or if you want to translate it to machine learning and fitting, you'd say 2 features which are, either 100% correlated or exactly the same. Then, in fact, you get your choice. They might not be the same, right? So, and I don't think that matters, right? We're just saying what is the best. This says you may pick 4 features, right? And it says what's the best fit you can get, right? Usually there's a unique set of 4 features that does that, but if there's not, then I don't think it matters. It's the same thing. I don't know if that made sense. Didn't totally make sense to me, so, but anyway, it's fine. Okay. Here's like sparse signal reconstruction, right? So, so these are just the kind of standard things. Actually, a lot of people would square this. It has no effect. It changes, of course, the parameterization with the hyperparameter gamma, but otherwise is the same, right? In fact, those are 2 scalarizations of what's really a bicriterion problem, right? So, and these are one. It's got all sorts of names. Here's just a quick example, right? So there's a signal with it's got a dimension 1,000, but there's only 30 non-zeros, and here's the exact signal. This is just a simulated example, right? And then I give you 200 random noisy measurements of these 1,000 numbers, right? And, so if you do an L1 reconstruction with, an appropriately chosen gamma, you basically get it, like exactly, right? So I think, 20 years ago when people were first seeing this, this is pretty stunning. I mean, nowadays, I think a lot of people have already seen this in undergraduate machine learning classes, and they're like, yeah, so what? Like, who cares? But you really should stop and actually reflect on this and think how cool it is. This is basically, somebody walks up to you on the street and says, I have 1,000 numbers I'd like to help you figure out. You go, cool, I'll be happy to help. You tell me, what measurements do you have? And you go, I have 200 measurements. You're like, oh, I'm sorry, did you say 2,000? Or did you get the two numbers different, right? Do you have 1,000 measurements and something like that, and 300 parameters you want to estimate? You go, no, I would like to estimate 1,000 parameters based on 300 noisy measurements, right? So, I mean, the correct thing to do in a situation like that is to walk away from that person. Maybe not turn your back on them, just walk away carefully and avoid them from then on, right? It's like someone walks up the street and says, I'm thinking of 4 numbers, they add to 12. What are they? You should avoid people like this, right? Because it's a nonsensical problem. Okay, fine. But then they say, but there's only 30 are non-zero. Then you'd say, that sounds like a normal thing to me, right? Because you think of like fitting and stuff like that as like data compression. And you go, cool, I have 300 noisy measurements to estimate, is that right? Yeah, 200 noisy measurements to estimate 30 things. That feels right. That's a sensible thing. You'd say, what are you doing? I'm fitting a model. How many parameters in your model? 30. How many measurements you got? 200. Sounds totally cool. Okay. But there's a catch. No one tells you which 30 of the 1,000 they are, right? And 1,000 choose 30 is a big number. Okay, right. Everybody following this? Okay. So what's amazing is it just kind of works, right? And I think one of the first packages for this, maybe 20 years ago, 25 years ago, was called L1 Magic. Was the name for it. So which was, now people don't care. But it is good to every now and then think how crazy this is that this actually kind of works. Okay, just for comparison, that would be the L2 reconstruction, right? Well, duh, right? If I walk up to you and say, please help me guess 1,000 numbers, I'll give you 300 noisy measurements. What did you think was going to happen, right? So this sort of fits with that. Okay, I'm actually going to skip this because I don't know, there's kind of, fussy things that actually tell you under some circumstances this actually does with high probability, actually work. I'm going to go on from that. Okay, we'll just go to the next part. Okay, so we'll look at a couple more examples that are pretty cool. So you could do the same kind of thing. We did total variation for a scalar signal, right? So the total variation is essentially the L1 norm of the derivative. That's rough, but that's what it is, right? It tells you how much, that's what it is. Let's just leave it that way, right? And the convex cardinality, thing you can do that's called the total variation. You do the same thing. And, we actually saw an example. I think, here's an example where, the top is some original signal, which has got smooth parts, but also these big jumps. The corrupted version is below. And then when you denoise it, you get things like this using L1 reconstruction, right? And you could sort of decide which value is right, which you could do by some kind of cross-validation or something. But, this is, roughly speaking, this looks like it's over-regularized. That looks like maybe it's under-regularized. And you might say that that's about right, or maybe somewhere even in between these two might be about right. Okay, and so this is used in, actually there was a famous incident in the 90s. I think this was used to reconstruct actually a lot of old wax recordings of like Caruso, the opera singer. They would have these wax drums, all scratched up and things like that. And to extract what something based on the total variation denoising would do would actually remove a lot of the noise, but actually preserve these sharp attacks, right? Because otherwise, if you did kind of the L2 version of it, it's just a low pass filter. I'm now speaking dialect, but sorry. And so basically, it would just come out muffled. Good news, noise is substantially reduced. Bad news, so is the actual content, right? But when you do total variation, you get something that's actually kind of cool. The attack of a drum beat when somebody leans into a snare drum, It's right there, right? So anyway, that was in the 90s, I think, which is kind of cool. So, okay, I will skip this because I think we saw that. One more example, but this is in 2D, right? So, and even this is a simplification, right? So, and I will make a comment about this a bit later, right? So in let's say that I have an image, like let's say I'm doing MRI reconstruction, right? And so I have all these values here, and a good here the total variation. It's actually given by, in the continuous version, it's actually this, right? It's f of, here, I can call this, I'll do this. It's this. There you go. That is what the total variation is in when you do this as in the infinite dimensional case, right? Very important here, this is not squared. So, as a matter of fact, there's a weird thing when you show this to someone. It's sort of like if you show someone VV, they just don't even see it often. So, many people, when shown this, their retina, I didn't even know where it happens in the optical cortex, but a 2 appears here. And then you have to go, so you have to actually emphasize this when you show this to people, because they're like, yeah, sure. Then they go to the next one, and something paints in a 2 here, right? Just because that's the traditional thing. You don't paint it in here. So that's total variation. Okay, so simple version of that here is to estimate this, we make a 2 vector, which is sort of, the x gradient is just the difference here, and the y gradient is this, right? Turns out that's actually not the way to do it. You get artifacts that align with the axes, and there's actually way cooler ways to estimate the gradient based on, well, I don't know, if you study PDEs or something, you get a little template, and you make a gradient here that depends on, like, these things. I think they call that a stencil or something, and there's some coefficients in there to map those 5 values to 2 gradient numbers. This is the space x gradient and the space y gradient. Everybody got this? And you can make those so that they are actually approximately rotation invariant, right? So you don't get the artifacts. I only mention this just, this is the main idea here. This is the crudest possible stencil or approximation of the space gradient of an image. Would be its x differences and its y differences. But you could do actually better. Okay, so this, you get something that looks like that with that very crude approximation. You get something that looks like this, and then you end up with something like that. Okay, so we'll look an example of this, right? So here's what happens is I have, this is probably tomography or something. So this is my original thing in 2D. I think it's a tomography problem, so I calculate line integrals through it, right? Which tell me all that, and then I reconstruct it. And if you use like total variation to do this, you do like, and this is again a case where you have eight times more variables to predict than measurements. So it's the same as the last one. You just reproduce it like pretty much perfectly. Actually, if you look closely, you'll see that there are weird artifacts, but that would be fixed if you did a fancier version of this approximation. Okay? And, again, if you just wanted to compare that, that's what the L2 reconstruction would look like, right? So it's not bad, right? It knows that, there were some line integrals that kind of went through the main part of it, came out pretty big. And from that, you would conclude there's something there in the middle, and it's basically a blob, right? So this is standard. I mean, a lot of people do other stuff now, but these are kind of like these were regularizers that were like a lot better than what people had before, right? So, okay. We're now going to mention a little bit about, just for fun, the idea of an iterated weighted L1 heuristic. And the way that works is this, is I start with all the weights 1 here, and I do L1. Then what I do is actually really cool. If xi is 0 here, I set the weight to 1 over epsilon. Epsilon's a small number, and that means it's really high, right? If x is big, I actually reduce the weight below 1, right? So basically what this is doing, this update here, is actually doing triage. It's basically who's going to live and who's not going to live, right? So if you're small or 0, your weight goes up And that means you're a prime target for being mapped to 0 in the next L1 minimization. If you're big, your weight is reduced, which means that basically, I mean, if I anthropomorphize, it means you've concluded that, you know, whatever x7 is going to be non-zero. And so you reduce the weight. This actually kind of combines polishing there, right? Because that's what polishing is, an extreme form of this. Polishing goes like this: solve the L1 problem. And like, you're 0, put an infinite weight on you. And that means you're never going to be non-zero, right? You're non-zero, you go put your weight to 0, meaning no regularization, and then you resolve. So polishing is an extreme version of this. This is like iterative soft polishing or something weird like that. Okay, so this actually works like quite well for a lot of things. Very few people know about this. I don't know why, but it's true that many people don't know about it. And you get a beautiful interpretation by doing something like this, which is very cool, right? So let's start with the actual card function, which looks like this. There's the card function. And someone comes along and says, well, I know a way I'm going to use an L1 heuristic. And they go, what's that? And you go, well, instead of your function, I'm going to use this function. How about that, right? And they go, that's not a very good approximation. And you go, yeah, but it seems to work pretty well, right? So here what you do instead is you write down, you have like you make a non-convex function that it looks close to this, and I'm going to write down what that function is. It's going to be this. I'm going to make a weird function that goes like this. Actually, over here it'll be like, you know, minus, I can subtract something, make it epsilon like this. But it's going to look like that. And that, you would say, that's a pretty good, that's a better approximation of this cardinality. Oh, by the way, people do this also with powers, which is kind of cool. So you do the square root. That's another one. You would here's the real thing. Sorry, this is like that. That's like that. And people would put like a square root here, right? And then they would write extremely annoying papers about, they would say LP approximation with P equals 0.5. You know, which drives me nuts because there's no such thing as an L.5 norm. Oh, even worse, people refer to cardinality as the L0 norm. So has anyone heard that? Okay, don't let that stand. If you are in a social situation and someone's L1 norm, say something like, excuse me, that's not a norm, okay? And if they say, oh, that's cool, sorry, I thought we were just like friends here or whatever, just casual, then you go, fine, but just to check that they know that. If they don't, then I don't know, leave the room or something, because you should not hang out with people like that. It's like people who talk about an over-complete basis. And you're like, what? Well, anyway, otherwise known as a set of vectors, right? So just, anyway, all right, fine. All right, so here, it turns out here you do something, you just linearize this objective at the current point, and then you get exactly this iterated reweighted heuristic, right? So so you can think of it as doing people sometimes call that sequential convex optimization. So that's when you have, you know, a term, a constraint term, a function that's not convex, and what you do is you approximate it by a convex function at each step and solve that problem, right? And this is an example of that, and it works like, you know, this works like quite well. Okay, so that's it. And I'll just show you some quick examples of that. So, I mean, here would be a baby example, right? Is we want to find a sparse solution in a polyhedron, right? Of a set of linear inequalities, right? So what we do is we start with the L1 heuristic, and yeah, you come back with something that has cardinality 44, whatever, it doesn't matter, right? So if you run this iterated L1 heuristic, these are the iterations, what you can see is like, I don't know, in 3-4 steps, you've got something with a cardinality of 36, right? By the way, for this problem, for fun, we just solved it globally, and the global solution is 32. By the way, that worked perfectly. It was a randomly generated example, because had the global solution been 36, this would be misleading, right? So this tells you everything. This example worked out perfectly to say exactly the honest and correct story, which is this is a really good heuristic. And if someone says, does it always get the global solution? The answer is, no, doesn't. And here's a perfectly good example, right? So, okay. So this is just a quick example of that. So you can use this in all sorts, once you understand about these methods, you can use them in very cool ways, right? Like, so here's a quick example is I have an AR model, so an autoregressive model. And what we're going to do is we're going to assume that the dynamics of the AR model, right, which is the A and the B, they change, right? I mean, this is like there's a lot of things for this, right? Where you want to fit a model, but it changes over time or something like that. And so what you do is actually something pretty cool. It's a weird idea, but here it is. What you do is you start by actually assuming that you introduce a number of variables. So if you were just going to AR2 fit, A and B would be constant, and they'd be two variables. And you'd have a bunch of data because you'd have t equals 100 or time steps or a couple hundred, and everything would make sense to fit an AR2 model. But here what you do is someone says, no, but my AR2 model is time varying. And you go, okay, cool. So you actually have a different A and B for each time period. Minor problem with that is you're now hideously overfit, right? At least 2 to 1, right? Because you've got, so it's not just that you can you can match something exactly. So you have to put something that some prior on A and B, right? You could have lots of priors. I mean, here would be one. A and B are increasing. I just made that up. Here's one. They vary smoothly, meaning the sum of the squares of the differences is small. Everybody got that? So that'd be a smoothly varying AR model, right? Here's another one. You have a piecewise constant AR model, meaning A and B are constant for various periods, then there's some shift, and they assume different values. Everybody got this? But by now, at this point in the class, you have all the tools to do, like, you could do all sorts of crazy stuff with this, okay? So you do this. So this is basically the regularizer, and this is the loss, right? So this is just a traditional square loss or Gaussian, if whatever you want, if V of t is Gaussian. Okay, so then this is a regularizer, which if you read it, you will understand completely, is a sparsifier for differences, changes in A and B. Everybody got that? So it's a sparsifier for the difference, which is basically saying I want piecewise constant. Okay, so yeah, here's a quick example. And so here's some data that was generated. Here's A and B. I mean, it doesn't matter. But, actually, since you see A and B, you can see it. They change at t equals 100 and t equals 200. And, if you look at your eyeball and draw a line here, you can look at that and look at that. And your eyeball, your spectral analyzer in your eyeball says something happened, right? And then you can, again, this is hard, but you could pretend, especially after you knew the truth, you could certainly pretend that you'd say, oh yeah, no, I can see that the spectrum is different. In fact, the autocorrelation changes. And then that's for people who have the ability to look at a plot of something and say what the autocorrelation is in their head. So there are people like that, right? But anyway, so you can see something happen in the 3 times. And the question is, how would we, from the signal on the left, how would we guess these changing coefficients, right? And here's what happens. If you just do that L1 heuristic, you get this dashed line here, right? And I mean, it kind of gets it. It's pretty good, right? I mean, you can see things like, it kind of got pretty close to where this change was. It was pretty good up there. But you see some weird little things like that. And this is kind of sad. That's weird. Okay. If you do this iterated L1 heuristic, you get that over there. And that's actually pretty good, right? That's good. And it's good. I swear I would have rerun this if it turns out it had nailed the actual times or the amplitudes exactly. I would have rerun it because that would have been sending the wrong message, right? But fortunately it did not. It's fine. This is kind of what you want to see. It does a pretty good job of doing this, right? But by the way, for for scalar AR2 models, no big deal, your eyeball can do it. But what if I gave you an econometric time series with 50 numbers, right? A dimension of 50, and I gave it to you monthly for 50 years, and you wanted to do this. Anyway, I guarantee your eyeball could not do it, okay? But you could, That's nothing. It's like 6-10 lines of Python. So I'm just saying, I'm showing you baby examples, but trust me, these are the exact same methods applied to much bigger and much more impressive examples. So, okay. Last topic is extension of matrices. This is actually very cool. So rank is kind of the natural analog of cardinality for matrices, right? And there's lots of ways to explain, to say that. And a convex rank problem is a problem that's convex except there are rank constraints. There's tons of these problems that come up all the time. And I mean, there's lots of connections to them, but it turns out the analog of the L1 norm is extremely cool. This is the dual of the spectral norm. The spectral norm is the maximum of the singular values. The dual of that, surprise, surprise, it's the sum of the singular values. By now, you should be seeing some of these patterns. It's, I don't know, like when you study music or something and you start hearing, you see themes and things like that, you should start seeing them. So now you know the dual of the spectral norm is the sum of the singular values, okay? So, which is cool. And guess what? It's a low rank. We don't have a verb like sparsifying, but it's a low rankifying. That's not a verb, but if it were a verb, we'd have that's a low rankifying regularizer, right? So lots of cool stuff. I mean, I give you one example, and now this is research from only 10 years ago. Like, suppose I give you some samples from a Gaussian vector, Gaussian, but I'm going to give you the prior that the inverse of the covariance matrix, which is the precision matrix, is sparse, which, by the way, has a beautiful interpretation because sparsity in the precision matrix, in the precision matrix, corresponds to conditional independence, right? So basically says, here are these things. My prior is that it comes from a sparse Bayesian model because that's exactly what that is. So, by the way, if you don't know what I'm talking about, well, you should probably learn this stuff because it's really cool. If you do, then that's fine too. So, okay, then you would know what to do. You maximize log likelihood minus the dual norm of the precision matrix, right? And you would be about 8 to 10 years ago in research, right? So it's kind of cool. So yeah, you're very close to sort of the boundaries of research here. So okay. I think maybe I'll even skip factor modeling as an example, and I'll quit there. And now we want to switch to something else, which is going to be. Let's switch over to here. Yeah. So okay. So at this point, the class is over. So we're done. I mean, not for you actually for that matter, or us, but you'll finish your homework 8 by tomorrow. Hopefully you'll get a working barrier method or something like that and then feel good about that. You should feel good about that. Then you have a week to kind of poke through all the material. You really should go back for fun and like read, I don't know, a couple of sections in duality or convex functions. Because now, I mean, you've been living with them for 9 weeks. So it should be like the first time you saw this and you thought log determinant or something like that, or the min of the square root, it probably looked pretty weird. It should look very familiar to you now, I hope, right? Okay, so you're gonna have a whole week of kind of just letting all this stuff process and all the neural links formed and stuff like that. So what I want to do now is just actually talk about just some of the super high level like main ideas in the class, right? So this, first of all, there's a ton of problems in any sort of mathematical area that reduce to optimization, right? So, engineering, design, data analysis and statistics, economics, management, all of these things, they're just optimization problems, right? I mean, frankly, that's a tautology or something. I mean, like, so of course they're all optimization problems. That's not an interesting statement. I mean, it's an interesting way to think about things, right? Like, it's actually, I think it's actually a super clear way to do it. Like, you go into a situation and people are coming at you from 4 different ways, telling you, oh, there's this and we have to do that and these constraints, and forgot about, oh, there's regulatory, blah, 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 and you're like, and you just sit down and you say, okay, wait, sorry, what are the things you're allowed to mess with? These are the variables. What are the things that are not, that are non-negotiable? And they would say, well, these, and those are your constraints. And then you'd say, what would make you happy? Now, they probably are going to mention 2 or 3 things, right? And then you know you have a multi-criterion problem. And you'd say, cool, I will scalarize it with a bunch of weights, and we'll play with those later to see how happy we can make you. Everybody following what I just said? So it's actually not a bad way to organize your thoughts when you get into something. There's people coming at you from 50 different things, and they say, oh, whatever, don't remember, remember rule 144B, and remember the, the Basel requirements for capital. And you're like, well, anyway, so it's just a very good way to actually just do anything, right? Not just there, but actually any field. Okay. Okay, so, basically, tractability, I mean, roughly speaking, but I mean, some people get really weird about this. Tractability, the problems that are tractable are the ones which are convex, right? And there's people that get weird and extreme about this. I'm not one of them, but so they would actually go through the undergrad CS course, and they'd say, you can find the shortest path in a graph from here to here. That's polynomial time. That's not a convex problem. Well, the answer is yes, it is, right? It turns out it's one where the relaxation has 0 duality gap. Right? Or they could say, I can take the singular value decomposition, that's not convex, and then it's even weirder. They would say, oh, it is, because the dual of that has 0, that's a non-convex problem with 0 duality gap. This is getting weird because it's just, we know how to do that, right? And of course, the other thing is we shouldn't get too bent out of shape about it, because in, 95% of applications, when you're solving an optimization problem, that's just a surrogate for what you really want. And that's actually something good to keep in mind, right? So, if you're doing machine learning, you don't care about minimizing a loss plus a regularizer. You want to have good predictions on data you've never seen before, right? If you're making a drone trajectory and you're running MPC or something like that, you don't care about solving whatever optimization problem you want it to follow the trajectory and use as little fuel, or in that case energy, as possible. Everybody see what I'm saying, right? If you're doing finance, you just want to make money without taking risks. If someone chooses to solve some silly convex optimization problem to do it, good for them. But you're not paid, we should just all bear in mind that in almost all applications, the optimization problem you're solving is actually just a surrogate for what you really want. So that's an important thing to remember. And when you think about that, then you realize, it's not that big a deal if you can't solve a problem globally, right? It is, it's perfectly cool if you can, right? But if you can't, it's just not that big a deal, So, if someone took your circuit design and reduced the dynamic power consumption by 20%, you're happy, right? Maybe you think could someone do it by 30, but you're just happy it's 20, you just reduced it 25%. So I'm just saying, we shouldn't get too hung up on this. Nevertheless, tractable is not a bad thing. So, to be able to say, I can solve this problem exactly, there's a lot of benefit. One benefit is there's no babysitting of the algorithm, right? When you have, close your eyes and think of any place where people widely use non-convex optimization. Anyone here can think of a bunch of those, right? It turns out actually quote, solving those problems, which you're not actually doing, is actually an art. And somebody says, oh, no, you should be using this and that, and you should change the learning rate and blah, blah, blah. And you just don't, that's just all short-circuited, you just don't have it, right? Or what's your initial, like you asked, what's the initial condition, right? That's a pretty good circuit design, but what was your initial design, right? And the point about this is that's just short-circuited. There's no such thing. You don't have any of that. It's just all gone, right? The other advantage, of course, being the fact that they can be made unbelievably reliable, and therefore they can be embedded. So they are embedded in control systems where they solve 1,000 QPs per second. And they do that for hours and hours and days, just forever. And it just works, right? And, try doing that with a non-convex thing. Because it's not going to take long before something fails to converge or something like that. Okay. So it turns out, a lot of applications that you've seen in this class, they can be formulated as convex problems. We go a little bit overboard on it because you're kind of in a little sandbox now. But once you finish the course, you can venture out. So it turns out most problems aren't really convex, but it turns out once you know these tools, you're going to be unbelievably effective at problems that aren't convex, right? Because someone will say, yeah, I want to do a trade list. You say, oh, but there's a minimum non-zero trade size. Like, I'm sorry, don't come back and tell me to buy like $300 worth of something. Minimum is 10,000. Everybody see what I'm saying? Either see the 0 or minimum 10,000. That actually happens like all the time. Okay. Once you know these things, you will figure out all of you could figure out a heuristic for that, and it would be extremely good. In fact, somebody just come up with a heuristic for that right now. I'm going to sell. Let's make it simple. I'm going to sell a bunch of stuff. I have 6,000 assets. I'm going to sell some, but here are the rules. Don't ask me to sell $300 worth of something. I mean, that's kind of insulting, right? Make it something. Make it 10,000. It's either you don't sell any or it's $10,000 worth. Somebody come up with a heuristic right now. And the rest of the problems I've got, transaction cost, risk, blah blah blah. I don't know. So somebody give me an example. Well, how would you do it? I say you could do it right now. Well, maybe after some reflection. What would you do? What's the first thing you would do in that situation? Let me describe it a different way. Somebody comes into you and they're ranting and raving and they say, here's what I want you to do. And they list off 12 constraints and objectives which are convex and one that's not. Do you have a suggestion for me? It's a street fighting suggestion. What is it? What would you do?
Relax the last one.
Yeah, relax the last one, which means, let's be brutally honest. How about this? How about just ignore it? So that's kind of what that's a strong form of relaxation, right? So you solve it without it. Okay, yeah, you can put an L1 norm in there. That's fine. Let's put an L1 norm in there, and then you look at all your trades, and then what do? If they come out above $10,000, they're fine, right? If they're 0, they're fine. If they're in that weird dead band in the middle, they're not cool, according to your trading desk or something. Everybody following this? I mean, I could transpose this to any field there is, right? I guarantee you exact identical things happen. Like, here's one. A generator is either off and generating 0 power, or the minimum is like 10 megawatts. So it's either 0 or between 10 and 30 megawatts. End of story. So that's identical to this, right? Okay, so, all right. So what you do now is what you do is you solve it once, then you simply have a threshold and you decide which generator is on and which is off. Now you resolve with that as a constraint. If you're on, you're bigger than your minimum power. And let's make it 10 megawatts. If you're trading, you'd say, I'm going to sell more than anybody that came. If you're on, I'm actually selling you, I have to sell more than $10,000 worth. Everybody got this? And everything else is 0. That's 2 convex problems. This would work beautifully. It's a heuristic. But this is just an example to say that, we do stuff that's mostly just convex. But once you absorb all these tools, you will be extremely effective at things like that. Right, so, okay. All right. So, the theoretical consequences of convexity are, local, optima, or global. Duality theory is kind of awesome, right? Basically, I think of it as it's a completely systematic way to derive sophisticated lower bounds on the optimal value of a problem, which is kind of cool, right? In the case of convexity, they become sort of necessary and sufficient. I mean, not quite. There's a little asterisk, there's some constraint qualification, but that's fine. And it's super useful. Like, it allows you to do things like sensitivity analysis. It produces things like infeasibility certificates, right? When you come back and you go, can't do it, can't design it. Someone says, why not? You go, no one can. And they go, well, you can't, but I'll fire you in your group and I'll get a new one and they will be able to maybe. And you go, no, because I can actually easily prove that no one can do it. Everybody following? That's a certificate of infeasibility. Okay? So that's cool. I mean, if you care about the worst case complexity theory, then there is one, right? So that's fine. The practical ones are actually, I think, much more interesting, right? So, basically, if a problem is convex, you can solve it, right? I am aware of no situation where someone proposed a convex problem, that they couldn't end up, not all of them are going to work with CVX pi, right? But people in machine learning, they were like, Excuse me, I have a billion samples. So, and by the way, 100 million parameters. So it's not working, right? People figure it out. In that case, you use these other, methods like subgradient methods or something like that, right? People for images and you can do a lot of that stuff too. It's all fine. Anyway, so this is the basic idea. But for normal sized problems, I mean, if you're not doing, images or giant things or, or handling video or something like that, then, you're within striking distance of these kind of easy to use tools, right? So the the implications of things like CVX-Pi are immense, right? And I can tell you specifically why you should be extremely grateful that you're taking this in a post-CVX-Pi world. Because I'll tell you how it worked before that. Here's the way it worked. I'd go into my office, be a bunch of some grad students there, and I'd say, I've got this unbelievably good idea. Here's how we're gonna solve this convex problem, and that's gonna be it's gonna work really well for for some application. And they go, cool. Then here's what would happen. I would go home, have a nice dinner, that kind of thing. Grad students would sit around and implement some, and it's not easy. I mean, they would have like Mosaic or some commercial solver, who knows, or some other one. They'd be writing like C, C++, and basically stuffing matrices by themselves. Everyone following this? It would not be fun. I would come in the next morning all well rested and I'd say, hey, how'd it go? And they go, oh, we implemented it. And I go, cool. How's it work? And they go, not too well. And I go, oh, well, I got another great idea. So so I think actually it's basically like grad students who should be most grateful for the existence of these high level tools, right? Because they're I believe the chief beneficiaries. Okay, so how do you use it? I mean, people have different ideas about this, but these are just sort of mine. Basically, I'd start with this rapid prototyping, right? So you start with really simple models, small problem instances, and you can use some inefficient method. I mean, it doesn't matter. By the way, if you don't like the results there, then you save, if someone else is saying like, it's never gonna scale, what are you doing? If you don't like what it does with problems with 1,000 or 10,000 variables, then why on earth would you think you're gonna like what it does for 1 million or 100 million, right? By the way, there's some people, I got yelled at by someone at Google who once said, that's so wrong. He said, the things we work on, the interesting things emerge at scale, right? And that's, supposed to sound really deep and all that. And it's true, okay, but it's fine. So, and they no, we implement at scale. And I'm like, well, good for you. So I'm just saying there's diversity of opinions about how to do this, but anyway, you heard mine. And there's others who say that, okay. So, you can always do cool stuff. Like you can work out and simplify the optimality conditions in dual. That's, honestly, in most cases, that doesn't actually have any practical use because you're going to solve it and stuff. So you don't need to worry about that. And in some cases, there's some rare cases, but it's actually kind of interesting because it's kind of cool to say, hey, guess what? We get prices automatically. We get energy prices, in 15-minute intervals at all these different nodes. There you go. This is like $87 per megawatt hour from 2 to 2:15 p.m. at this node, right? That's so there are cases where it's actually really useful to understand the dual and work it out. In other cases, though, it's mostly there to interpret actually to impress your friends, right? Because then you can sound really, you don't really care. You would say, oh, I'm designing this thing, and that you'd say what the dual is, and they go like, God, that's awesome, that's cool. Did you use that to solve it? And you're like, no. But anyway, so, okay. So it turns out, once you understand all the convex stuff and are pretty fluent with it, you can do all sorts of crazy stuff, like by repeatedly forming and solving a convex approximation. We actually just did that over here, right? So these are just super good methods to know about. Yeah, and there's a lot of street fighting tricks, and someday I'm actually going to put maybe a lecture together on street fighting tricks. I'd had everyone sign an NDA saying that under no circumstances could they divulge where they learn these things, and that I would deny it if they pointed at me. Anyway, so I haven't done that yet, but there's really cool. I mean, I just give you one for fun. Here's an example. you go on an internship and someone says, generate me minimum fuel trajectories that move this thing from here to there. And you go, cool. Please tell me about the fuel use. And they go, oh yeah, no problem, because an intern last year. And then they dump something this thick on your desk or whatever it is, right? And they go, yeah, that's it. And then they start talking about like thermodynamics and, you know, N1 and N2 and these turbines and their reflux and the pass and all. And you're like, bah, like, anyway. Then you say, do you have a simulator for it? And they go, yeah, we do. Okay. So then you set up a script to simulate it, and you find out that the fuel use looks like this. You know, when you ask for, this is the thrust you're requesting, and this is at idling, and it looks something like this. It goes like that, and then there's actually something weird like that, and then it goes like that, and then it goes up like that. Everybody got this? Right? And then someone who knows the details would say, well, I know why, because, okay, when you get up to this amount of thrust, they open these valves and there's some, I'm just making this up. There's some gas that flows over these fourth turbines. And I don't know, anyway, but it would look like that, right? This would be this you got from a simulator. Everybody following this? Okay. What would you do now? And now we're in full street fighting mode. What would you do? Well, first thing you do is you'd say, it's not convex. Okay? I want a suggestion. Yeah, get a convex surrogate. Want me to make one for you? Okay, here's my convex surrogate. Ready? You just kind of go like that or something. It's fine. Okay? Now you solve the problem quickly. You could even fit this either by eyeball. If it's in one dimension, you do it by eyeball, and then you just solve it with this thing. It's fine, right? So everybody following this? So I'm just saying that, that's not now, not until you get your actual stamped certificate saying that you are, you're now no longer a trainee or something. But when you get that certificate, you'll be allowed to. So don't do this for the next 10 days. But after that, you have license to do stuff like this, right? So, okay. Everybody following this? So, okay. So there's a whole lot of stuff we didn't cover, and that's actually something I want to talk about like what's next. So we didn't talk about like this whole area of like subgradient methods, stochastic subgradient methods, and you've probably seen this in a machine learning course or statistics course, I would imagine, right? And absolutely fascinating. So a lot of stuff there. Actually, all of these are taught in, I guess, several courses, and that's the next thing we're going to talk about. So there's 364B. I think I actually have a list of courses here, but it's like way out of date. Yeah, so this is completely and hideously out of date, but that's fine. I'll leave it up here anyway. So you have a couple of, you may never want to take a course in this area again. But if you did, I'll point you to some places, right? So one is 364B, which is we cover a lot of material in that. That's super useful. It's not as linear in its dependency graph as this class, right? This class is you do this, then you do that, then you do that, then everything. It's just very linear. That one is once you know about subgradients, then the dependency graph gets wide. And there's a lot of choices of topics. But they're just super good things actually for implementing. I mean, some of the best things you would learn in 364B would be how to solve relatively big problems that would either take way too long using CVXPy or just not even work, right? So if you were doing image reconstruction or if you're reproducing stuff from video data, right, where it's just too big. I'm sorry, you can't plug that in and stuff like that. You'd learn how to do that. You'd probably write it in Torch or something like that, but you'd learn very effective, simple methods for that. So that's fun. You'd learn about cool things like distributed convex optimization, which is like super cool. I'll tell you how that works. You're sitting on some data, and you're hospitals, and you have some data too. And I want to fit a model, like I don't care, a logistic regression model of something, right? Like, if what's the likelihood this person's going to develop sepsis? There we go. Okay. So you have a bunch of data. You have a bunch of data. Obvious thing to do is I'd say, could I please have all your data? So I would collect all your data, and then fit a model, right? The way it works in distributed convex optimization is very cool. It works like this. I don't get your data. I don't get your data. but I coordinate you. So I'd say, you fit a logistic model on your own data. Everybody got that? Then all you do is you send your models to me. I do very small amount of computation, and I send a, oops, sorry about that. And I send a message back to you. You plug another term into your models and refit. And this goes 10 steps, order magnitude. And at that point, we've converged on the same model. You actually have no idea how many other hospitals I'm talking to. But guess what? We just, together, solved this problem that's identical to had I collected all of your data in one place and done it all once. Anyway, everyone get that? That's in 364B. It's actually in a couple of other things, but these are like pretty cool things. We didn't talk about it at all here. Not surprisingly, it uses like ideas like duality and stuff like that. Okay, and the other one is 392F. Is that right? So that's taught by Ernest Ryu. He's a professor at Seoul National University. Just wrote a beautiful book on monotone operator methods. It's going to be, it'll be a little more mathematical than this one, but it's going to be a weird thing because it will look like math, but in fact, everything in it is like extremely, it's very close to extremely useful things. Like if you took that course, actually kind of stayed awake through the math, you're just one like torch implementation away from actually an extremely good, very large scale solver for something. Everybody got that? So that's a cool thing. So I think, let's see, what I'll do now is, so I have to thank the TAs. You probably, I don't know if you have any idea like how much is going on behind the scenes. A lot of it is chaotic and you wouldn't want to know, but mostly it's just a whole lot of work just making sure like scripts actually still work with updates and CVXPy and all sorts of other stuff. So anyway, it'd be impossible without tons of help from them. Yeah, and I think we're done. You've mostly survived, I think. So yes.
Oh,
sorry, I should have mentioned Michael's class.
Yes.
Yeah. Okay. So other things I would point you to that'd be very cool is actually I just point you to all of Michael Kokendorfer's classes, all of them. So and books. So it's simple. Just read them, take the classes, whatever you want. They're going to be extremely good. They're quite different, right? So they're more we focused on one idea like convexity and for that matter very very small number of methods. His courses are more like we're going to do optimization. We don't care if it's convex, non-convex, and we're going to look at multiple methods to do it. But just beautiful, clear book, incredibly good classes. So I would actually strongly urge you to look at those. Right? Some people don't know about them because I guess they're listed in Aero-Astro, and then maybe they're cross-listed in CS as something. So people in CS know about it, but I think many others don't. So I would strongly recommend those. So, all right, cool. All right. So I actually think we're done. So our experience, by the way, is after you take the final, the nightmares recede after a couple of weeks after that. They recur for the next year or so, but it's fine. We don't know of any long-term problems with that. So good. Have fun and good luck, and see you in office hours or something. Good.